In my last video, I talked about peroxide acids and bases. Today, I'll be talking about acid dissociation constant and the position of equilibrium in acid-base reactions. So, the acidity of any organic acids or base would involve the measuring of equilibrium constant. If I looked at the dissociation of acetic acid in water, as an example, I have C double bond O, OH, plus water in equilibrium with my acetate ion. So I need to define the equilibrium constant of my reaction. So let's assume a general reaction between acid and water to give me hydronium ion, and the acid will be deprotonated. Now my equilibrium constant would be my product over my reactants. So my products in that case would be the concentration of my products, H minus, multiplied by the hydronium ion over the concentration of my acid multiplied by the concentration of water. Because I know the concentration of water, I can just move this the concentration of water and multiply it by the equilibrium constant, my equilibrium constant, and this will be my dissociation constant. So my dissociation constant is actually the equilibrium constant multiplied by water. So if I move this concentration that side, this means my dissociation constant would be equal to the concentration of the hydronium ion multiplied by the concentration of the deprotonated acid over the concentration of my acid. Now, if I need to express my dissociation constant, I will find that it is so small and mostly negative value. This is why in most cases I express it as the minus log of Ka. So my pKa would be the minus logarithm of 10 multiplied by the Ka. By that I will have a more reasonable values that I can deal with. Now let's talk about general reaction where an acid would react with water, where my acid would be deprotonated and the water will accept the proton of the acid. Now if I looked at my equilibrium constant will be my product over my reactant. This means the concentration, the equilibrium constant K equilibrium would be the concentration of my deprotonated acid multiplied by the concentration of my hydronium ion over the concentration of my acid multiplied by water. Because I know the concentration of water, I can just multiply, and it's very small, I can multiply the water concentration multiplied by the equilibrium constant, and this will give me the acid dissociation constant. So the acid dissociation constant is actually the equilibrium constant multiplied by water. In that case, I will have Ka equal to the concentration of my deprotonated acid multiplied by hydronium ion over the concentration of my acid. Because the Ka value is negative most of the times, this is why I need to convert it to more reasonable numbers that I can deal with. This is why usually I don't deal with the dissociation constant. Instead, I deal with the pKa, or the exponent of the equilibrium constant, and that would be equal to minus the logarithm, 10 logarithm of Ka. We have to know some remarks about the exponent of the acid dissociation constant. First, if it is a large value of pKa, this means my dissociation is very weak and my acid is very weak, because I take pKa is actually equal to the minus logarithm of my dissociation constant. Also, if I have a small value of pKa, this means I will have stronger acid because I will have stronger dissociation. My weak acid would form a strong conjugate base, and my strong acid would form a weak conjugate base. If I looked here at this table, I could see that the weaker the acid here, this means I have large pKa values. While moving down this table, I could see that I have a negative value of pKa. This means I have very strong acids, and for conjugate it's just the opposite to that. So I here my strong acid would form a weak conjugate base, and my weak acids would form a stronger conjugate base. Now let's look at this example. For each value of Ka, calculate the pKa and determine which compound is a strong acid. So first, if I looked at the pKa of acetic acid, it would be equal to the minus logarithm of 1.74 multiplied by 10 to the power minus 5. This would be equal to 4.8. If I calculated the pKa of chloroacetic acid, it would be equal to the minus logarithm of 1.38 multiplied by 10 to the minus 3. If I use my calculator, I find out that the value is equal to 2.9. Here I have 4.8 and here I have 2.9. So 2.9 is less than the 4.8. And remember, I told you that the larger the pKa, the weaker the acid will be. This means my chloroacetic acid is a stronger acid than the acetic acid. So if I need to determine the position of equilibrium acid-base reaction, I have to remember is what I can deal with is that dissociation constant, or the acid dissociation constant of my compound, or pKa. pKa is exponent dissociation constant of my acid. So I can get the value of this part and I can get the value of this part. As for bases, I cannot deal with them. So if I have complete dissociation constant like HCl, it's simple and I have complete dissociation. But if I have something like acetic acid, I will have sort of equilibrium. This equilibrium means the formation of acid and conjugate acid are in equilibrium. Both of them exist in my solution. So to be able to calculate the equilibrium of the acid-base reaction, I need first to my equilibrium constant would be equal in my first step the product over my reactant, which is the concentration of the conjugate base multiplied by the conjugate acid, which is pH plus, over the base and multiplied by the acid. Now if I multiply, because I cannot find the value of those together, I can just multiply it by hydronium ion on both sides. I'm just showing you how we the revision of this equation, but what we need is actually the last equation that we are getting. So now if I reorganize my equation to multiply this part by this value and this part by this value, this means it will be equal to A minus multiplied by my hydronium ion over, I will leave this part on that side, and I multiply it here. I will take that side alone. My conjugate acid and in the denominator I will take my base multiplied by the hydronium ion. If you looked at this value, it will remind you of the actually it is equal to the Ka of my acid, and this part would be the key value of my dissociation constant of my base. So I can just put this value, and instead of this value I will just write so K equilibrium would be equal to KHA, the dissociation constant of my acid, over the dissociation constant, if you looked at this one, of my conjugate acid. Now if I use the exponent for more reasonable numbers, the exponent of my equilibrium acid base reaction would be equal to the exponent of my acid minus the exponent of my conjugate acid. So this is what I'm interested in, this last equation, where is the acid minus the conjugate acid, the exponent of my acid minus the exponent of my conjugate acid. So if I looked at this equation, I could see that I am dealing with the acid exponent of my acid minus the exponent of my conjugate acid, and because I take the minus logarithm of my K equilibrium, this means if I took the antilog of my exponent, I will arrive to the K equilibrium of my reaction. In acid-base reaction, I have to remember the position of equilibrium always favor reaction of a strong acid and a strong base to form weaker acid and weak base. Now for ionization, in general, in what we call a physiological pHs, the pH between 7 and 8.5, we name it as a physiological pH. This is what happens in the human body, or the pH in human body. So if I have something like acid, the acid will substantially deprotonate if the pKa is lower than my pH. So I can expect, if my acid exists as this form or that form according to my pH and pKa. My pKa for something like carboxylic acid stands between 4 and 5, and because I have physiological pH between 7 and 0.8, this means my pKa is less than this value, the value of pH. This is why the form that would be presented as physiological pH would be that form. And if I have something like base, like amino group, in that case I have pKa value higher than my physiological pH between 7 and 8.5. This means that my compound would favor that the protonated structure more than the deprotonated one. If I have something here like quinidine usually, if it is found at physiological pH, I will have the protonated part. So for acids, the deprotonated form would occur in physiological pH, but for base, the protonated form would exist in the physiological pH. Now, what if I have a molecule that contains both acid side and base side? At physiological pH, the deprotonated of the acid would be favored, and protonated form of my base would be more favored. Now let's look at this exercise. In this exercise, I need to predict the position of the equilibrium and to calculate the K equilibrium in the acid-base reaction. Now I'm provided you here with the pKa value for the phenol and the carbonic acid to make it easier for you. If you look here at the direction of the values, you could find that this value is large. This means this is a weak acid, and this one would be stronger. So we said that the reaction would favor the direction where the strong acid would dissociate to form a conjugate base. So the direction of this reaction is actually favored in that direction, left direction. If I need to calculate the pKa equilibrium, this means I will the reactant minus my product, the conjugate, the acid minus the conjugate acid, 6.36. This means it is equal to 3.59. Now if I need the K equilibrium, this means it's gonna be 10 to the power minus 3.59. This value is equal to 2.27 multiplied 10 to the minus 4, because you have to remember that K equilibrium is minus the logarithm of 10 to the power pKa, which is, if you flip it to the other side, this means my K equilibrium is 10 to the power my pKa, K equilibrium. In the second example, I provide you here with the pKa of the acetylene and the pKa of the ammonia. So if you try to get the value of pK equilibrium, first let's look at which is stronger. So these have the lower value than this value. So the pKa here is lower than of 25 is lower than 38. This means this is stronger, and my reaction would favor to be moving to the right direction, because we said that the reaction would favor the dissociation of my strong acid. My pK equilibrium would be equal to the acid minus the conjugate acid to give me minus 13. My K equilibrium would be equal to 10 to the power minus 13. By that we came to the end of second part of the acid-base reactions in organic chemistry. Thank you and goodbye.